This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I have one very short handout for you today. It is the handout that has two problems that we'll be going over during tomorrow afternoon's discussion section. Remember, we don't have it at 3:15. That was just last week to accommodate what I assumed would be a large audience. It's at 4:15. It's actually permanently in the room down the hall in Gates B03. Okay, so I'm not teaching the section. Samaya, who I think is here, who's handing out the handout, so look for that guy tomorrow at 4:15. Both of these are old exam problems, so they're certainly good problems to understand the answers to. And if you're not going to watch section or attend, just make sure you at least read through the handouts. You may very well be able to do the problems yourself, and if so, then that's fine. But if not, make sure you watch the discussion section at some point. Okay? When I left you on Friday, I was third way through the implementation of an int-specific stack. So there's nothing technically CS107 level about this, except for the fact that we're being careful to write it in pure C as opposed to C++. Now, if you remember the details from Friday about the interface file, the functions are, I'll talk about those in a second. We actually expose the full struct. There are no classes, and there's no public and no private, so everything is implicitly public in the .h. That's a little weird. C++, when you learned about classes and objects, it was all about encapsulation and privacy of whatever could be private. We can't technically do that in C, although we can certainly write tons and tons of documentation saying, just pay attention to the type, use these functions to manipulate it, and pretend that these are invisible to you. Okay? You more or less operate as if this is a constructor, a destructor, and methods, but they happen to come in pure top-level function form, where you pass in the object, or the object's not the right word, the structure being manipulated. So stack new is supposed to take the struct, one of these things, addressed by S, and take it from a 12-byte block of question marks to be logically representing a stack of depth 0. This is supposed to kill a stack at that address. This is supposed to increase its depth. This is supposed to pop something off. Okay? I wrote stack new and stack dispose. I certainly wrote stack new. I'm forgetting about stack dispose, but I'll write them really quickly right now. This is the .c file, stack.c, void stack new, stack, I have these three things. Stack log length is equal to 0. That's because the stack is empty. I'm going to make space for 4 elements. And then I'm going to go ahead and allocate space for 4 elements using C's raw dynamic memory allocator called malloc. It doesn't take anything related to a data type. At least it doesn't know that anything related to a data type is coming in as an argument. You have to pass in the raw number of bytes that are needed for your 4 integers, and that's how you do this. All that malloc feels is an incoming 16. It goes to the heap and finds a figure that's that big, puts a little halo around it saying it's in use, and then returns the base address of it. Okay? I told you to get in the habit of using this assert macro that was mentioned in a little bit in assignment 1, just to confirm that a lems is not equal to null. If malloc fails for some reason, it rarely will fail because it runs out of memory. It's more likely to fail because you called free on something you shouldn't have called freed on, so you've messed up the whole memory allocator behind the scenes. That's a good thing to do right there because it very clearly tells you where there's a problem, as opposed to it just seg-faulting or bus erroring or crashing in some anonymous way, and you have no idea how to backtrace to figure out where the problem started. Okay? As far as stack dispose is concerned, this is trivial, although there's one thing I want to say about it. Actually, 2 things I could think of. I want to go ahead and do the opposite of malloc. This corresponds to operator delete from C++. I want to free S arrow lems so that it knows that whatever figure is identified by that address right there should be donated back to the heap. That's just what I mean when I talk about free right here. Some people question whether or not I should go and actually free S itself. they ask whether or not that should happen. The answer is no. Nowhere during stack new did you actually allocate space for a stack. You assumed that space for the stack had been set aside already and that the address of it had been identified to the stack new function. Does that make sense to people? Okay, so you don't even know that it was dynamically allocated. And in fact, the sample code I wrote last time declared a stack called S as a local variable. So it isn't dynamically allocated at all. So you definitely, in this case, do not want to do this. The other thing I want to mention is that regardless of whether or not the stack, at the moment this thing is called, is of depth 0 or of depth 4,500, the actual ints that are held inside the dynamically allocated rectangle of bytes, there's no reason to zero them out, and there's certainly no freeing needs held by those integers. Okay? I say that because just imagine this not being an int stack, but imagine it being a car star stack where I'm storing dynamically allocated C strings, Freds and Wilmas and things like that. Okay? If I did have that, in the case of the car star, I would have to for loop over all of the strings that are still held by the stack at the time it's being disposed and make sure I properly dispose of all of those strings. Does that make sense to people? Okay, I don't have any of that with the int-specific version, but the reason I'm saying this is because we're going to have to accommodate that very scenario when we go generic on this thing and just deal with blobs as opposed to integers. Okay? The most interesting of the four functions is the stack push, and it's interesting not because of the algorithm to put an integer at the end of the array, but the algorithm that's in place to manage the extension of what's been allocated to be that much bigger because you've saturated what's already there. I chose an initial allocated length of 4, so I'm certainly able to push 4 integers onto the stack and not meet any resistance whatsoever, but if I try to press a 5th in on the stack, it has to react and say, I don't have space for 5 integers, I better go and allocate space for some more, copy over whatever's been pushed, and dispose of the old array to make it look like I had space for 8 or 16 or 1024 or whatever. Okay? So the implementation, assuming I do have enough space, would be this simple. Stack, push. Pushing onto what stack? The one that's addressed by this variable called S. What number am I pushing on? The one that comes in via the value parameter. Let me leave some space here for what I'll inline as the reallocation part. But if there's enough memory, or down here I can assume that there's definitely enough memory, I can do this. S arrow allems of S arrow log length equals this value. Okay, think about the scenario where the stack is empty. The log length happens to be 0, which happens to be the index, the index where you should insert the next element. Okay? Once I do this, for the next time, I have to go ahead and say, you know what? The log length just increased by 1. Not only does it tell me how deep the stack is, it also tells me the insertion index for the very next push call. Okay? It isn't that simple. 80% of the code that gets written here has to deal with the 1 in 2 to the n time scenarios where you actually are out of space. Okay? If it is the case that S arrow log length double equals S arrow alloc length, then as an implementation you're unhappy because you're dealing with a stack and a value where the value has no home in the stack at the moment. I'm trying to press on a 7. Let's say that S points to this right here, and the logical length and the allocated length are both 4, and I've pushed these 4 numbers on there. The client doesn't have to know that there's a temporary emergency. So right here, I'm just going to react by saying, you know what, that 4 wasn't big enough. I want to go ahead and I want to, without writing code yet, I want to basically reallocate this array. Okay? Now I say reallocate because there really is a function related to that word in the standard C library. In C++, you'd have to go ahead and allocate an array that's bigger. You don't have to use a doubling strategy. I'm just using that as a heuristic. to allocate something that's twice as big, you'd have to manually copy everything over. And then you'd have to dispose of this after setting a lems equal to the new figure. Okay? Turns out C is more in touch with exposed memory than C++ is. So rather than calling malloc yourself, you can call a function that's like malloc, except it takes a value that's been previously handed back to you by malloc and says, please resize this previously issued dynamically allocated memory block. That is this. Well, let me just write one line right here. I want to take alloc length, and I want to double it. I could do plus equals 10, I could do plus equals 4. I happen to use a doubling strategy. And then what I want to do is I want to call this function. Deallocate these, so I have space to write code. S_lems equals this function called realloc. There's no equivalent of this in C++. I'll explain in a few weeks why there isn't. But realloc actually tries to take the pointer that's passed in, and it deals with a couple of scenarios. It sees whether or not the dynamically allocated figure can be resized in place because the memory that comes after it in the heap isn't in use. Does that make sense to people? There's no reason to lift up a block of memory and replicate it somewhere else to resize it if the part after, I guess I erased it, I didn't mean to, the part after the currently allocated block can just be extended very easily in constant time. The second argument to realloc is a raw number of bytes, so it would be S arrow alloc length times size of integer. I see a lot of people forgetting to pass in or forgetting to scale this by size of int. Even though they know to do it with malloc, they forget with realloc for some reason. I'm not sure why. It takes this parameter right here, it assumes it's pointing to a dynamically allocated block, and it just takes care of all the details to make that block this big. If it can resize it in place, all it does is it records that the block has been extended to include more space, and it returns the same exact address. Does that make sense? So that deals with a scenario where this is what you have, this is what you want, and it turns out that this is not in use, so it can just do it. So it took this address in, and it returns the same exact address. Well, you may question, why does it return address at all? In this case, it doesn't need to. However, it may be the case that you pass that in, and you want to double the size or make it bigger, and that space is in use. Okay? So it actually does a lot of work for you there. It says, okay, well, I can't use this, so I have to just go, and it really calls malloc somewhere else on your behalf. Just assume that's twice as big as this. Whatever bit pattern happens to reside here is replicated right there. The remaining part of the figure isn't initialized to anything because it's uninitialized, just like most C variables are. Okay? It actually frees this for you, and it returns this address. So under the covers, beneath the hood of this realloc function, it just figures out how to take this array and logically resize it and preserves all the meaningful content that's in there. Okay? It frees anything that if it has to move it, it does free this. It turns out realloc actually defaults to a malloc call if you pass in null here. So technically, you don't need the malloc call ever. That actually turns out to be convenient when you have iterative processes that have to keep resizing a node, and you don't want a special case of call to malloc the very first time. You could just call realloc every single time when the first parameter is null on the very first iteration. Okay? It's very easy to forget to catch the return value. If you forget to do that, then you refer to S_lems captures the original address, which may have changed, and you now, after this call, may be referring to dead memory that's been donated back to the heap manager. So it's very important to catch it like this. If realloc fails, it'll return null. So I'm going to put an assert right here. The one thing about realloc that's neat is that if you don't want to just end the program because it failed, it actually, if it returns null, it won't free the original block. It would only return null if it actually had to move it. Okay, actually that's not true. If it can't meet the reallocation request, it'll just leave the old memory alone and return null. In theory, you don't have to assert and end the program here. You could just check for null and say, okay, well, maybe I won't resize it. Maybe I'll just print a nice little error message saying, I actually cannot extend the stack at this time. My apologies. Please do something else. Okay. We'll learn a lot about how malloc and realloc and free all work together. They're implemented in the same file. Okay. They're implemented in the same file because even though we don't technically know how many bytes are associated, even though the actual blob of memory doesn't expose its size to you, like in a dot length field, like in Java. Somehow free, I guess I erased it. No, I didn't, up there. Free knows how big it is. Does that make sense? Well, there's cataloging going on behind the scenes, so it knows how much memory to donate back to the heap every time you call free. But I don't want to focus on that, okay? This right here, it doesn't get called very often. This doubling strategy is popular because it only gets invoked as a code block 1 out of every 2 to the n calls every time, once you get beyond 4. Do you understand what I mean when I say that? Because of the doubling strategy, it only comes up once every power of 2. 512 wasn't big enough? Okay, well maybe 1024 will be, and you have a lot of time before you need a second reallocation request. Okay, makes sense? Okay. There are a couple subtleties as to how this is copied. In this example right here, all of these little chicken scratch figures right there, they correspond to bit patterns for integers. So when I replicate them right there, I trust that the interpretation of those things as integers right there will be the same right there. Okay, so I really am moving, realloc is really moving my integers for me. If these happen to be not 4 integers but 4 char stars, that means the bit patterns that were here would have actually been interpreted as addresses. When it replicates this bit pattern down here, it turns out it replicates the addresses verbatim. This would point to that, that would point to that, this would point to that, this would point to that. You understand what I mean when I do that? When I dispose of this, it doesn't go in and free the pointers here. It doesn't even know that they're pointers in the first place, so how could it free them? So as this goes away, and these all point to where other pointers used to be pointing, you don't lose access to your character strings. Okay? Does that sit well with everybody? Okay, that's good. This is certainly the most involved of all 4 functions. Yep?
Can you explain the assertion again?
All assert is, it's, for the moment, just pretend that it's a function. It takes a Boolean. Its implementation is to do absolutely nothing and return immediately if it gets true. And if it gets false, its implementation is to call exit. And actually call exit after it prints an error message saying an assert failed on line such and such in file stack.c. Okay?
Well, actually, the contents, I was wondering why.
S arrow lems is not equal to null. You want to assert the truth of some condition that needs to be met in order for you to move forward. If realloc fails, it will return null. You want to make sure that did not happen. Okay, that's why there's a not equals there as opposed to a double equals. Okay? This isn't technically a function. We'll rely on that knowledge later on. It's technically what's called a macro. It's like a pound define that takes arguments. But nonetheless, just pretend for the moment that it works like a function. Yep?
In case where realloc has to move the array, is it now all and time?
Yeah, the question is, if realloc has to actually move the array, it is time consuming. It's even more time consuming than O of n. It actually involves not only the size of the figure being copied, but the amount of time it takes to search the heap for a figure that's that big. So it really can, in theory, be O of m, where m is the size of the heap. Okay? Does that make sense? Okay. Let me just quickly, just for completeness, write stack pop. It turns out it's not very difficult. The most complicated part about it is making sure that the stack isn't empty. This continues on this board right here. I have this thing that returns an int, stack pop. I'm popping off of this stack right here. No other arguments. Assert that S arrow loglang is greater than 0. If you get here, then you're happy because you have something you can pop off So go ahead and do the following. S arrow, log length, minus minus, and then return S arrow the lems of S arrow log length. The delta by 1 and the array axis are in the opposite order here. I think for pretty obvious reasons. You're effectively Control-Zing or Command-Zing the stack to pop off what was most recently pushed on. So if this came most recently, you want to say, I didn't mean to do that. Oh, and by the way, there's the element that I put there by mistake. Okay, that's what I mean. You understand what I mean when I say that? Yes, no? Okay. You could say you see this as demanding a reallocation request and going from 100% to a new 100% where the old 100% was actually 50%. You may ask whether or not if you fall below a 50% threshold that you should reallocate and say, oh, I'm being a memory hog for no good reason and donate it back to the heap. You could if you want to. My understanding of the implementation of realloc, because it wants to execute as quickly as possible, it actually doesn't, it ignores any request to shrink an array. Like, as long as it meets the size request, it doesn't actually care if it allocates a little bit more, okay? So it's like, oh, the size is 100 bytes and you just want 50. Okay, then only use 50, but I'm going to keep 100 here because it's faster to do that, okay? Does that make sense? Okay. There was a question that flew up in the back, I thought? Okay, very good. That's it, I think. With regard to the stack pop prototype right there, this sounds like a dumb observation, but it'll become clear in a second when we go generic. This particular stack pop chooses or elects to return the value being popped off. I can do that very easily here because I know that the return value is 4-byte figure. If this were a double stack, I would just make that leftmost in up there double, and it would just return an 8-byte figure. Okay. When I go generic and I stop dealing with ints and I start dealing with void stars, when I stop dealing with int stars and I start dealing with void stars, I'm going to have to make the return type either void star, which means I return a dynamically allocated copy of the element. For reasons that will become clear in a little bit, I'm not going to like that. Or I have to return void and return the value by reference by passing in an int star or a void star right here. Okay, that'll become more clear once I actually write the code for it. Okay, but we take advantage of a lot of fact that we know that we're returning a 4-byte figure here, so the return type can be expressed quite explicitly as an int. Okay, so now what I want to do is I want to start over, and I want to implement all of this stuff very generically. And I want to recognize that we're trying to handle ints and bools and doubles and struct fractions, and actually the most complicated part of it are char stars because they have dynamically allocated memory associated with them. Let me redraw stack .h, and we are going completely generic right here. Most of the boilerplate is the same. Type def, struct, and I don't want to commit to a data type. A lems. Now think about what I lost. I lost my ability to do pointer arithmetic without some char star casting. I also lost intimate knowledge about how big the elements themselves are. So I can't assume it's size of int anymore because it may not be that. It probably won't be. So I'm going to require the prototype of stack new to change to not only pass in the address of the stack being initialized, but please tell me how big the elements that I'm storing are so that I can store it inside the struct. The logical length versus the allocated length and the need to store that doesn't change. I still want to maintain information about how many of these mystery elements I have. I also want to keep track of how much I'm capable of storing given my current allocation. And there's going to be one more element that we store in a bit. Okay? So I'll leave that be suspenseful for the next 15 minutes and we'll come back to it. The prototype for the functions change a little bit. stack new, same first argument, but now I take an LM size. Void star, stack, dispose, stack asterisk S. That doesn't need to change. It's mostly the same, although we'll have something to say about what happens when it's storing car stars. Void stack push. My handwriting is getting sloppy. Let me slow down. Stack S, and then I'm going to pass in void star called a lem address. I can't commit to a pointer type that's any more specific right there, because it may not be an int star, it may not be a car star star, it may not be a struct fraction star. It just has to be some address that I trust, because of information that I'm holding, is pointing to an S arrow lem size figure. Okay? So there's that. This is the part that freaks people out. This is what I'm going to elect to do. I'll talk about the alternative in a second. But when I pop an element off the stack, I want to identify which stack I'm popping off of, and I also want to supply address. This is me supplying an address. I'm actually going to identify a place where one of my client elements that was previously pushed on should be laid down. Okay, it's like I'm descending a little basket from a helicopter. Okay, so somebody can lay an integer or a double or something in it, so I can reel it back up to me. Does that make sense? Okay. So void star lem address. And that's all I'm going to concern myself with. Okay? Yep.
Where is that struct named stack?
Oh, sorry, I just forgot it. It's right there. Sorry about that. Okay, so 70% of the code I'm going to write, it's going to all be the same. It's going to be slightly twisted to deal with generics as opposed to ints. Okay, but it's going to, rather than using assignment, which works perfectly well when you're taking one space for an int and assigning it to another int, we're going to have to rely on memcopy and things like that. Okay, stack new is not hard. Void stack new stack asterisk S int lem size. Same kind of stuff. S arrow log length equals 0. S arrow alloc length is equal to 4. S arrow lem size, let me do this up top, is equal to a lem size. S arrow lems is going to be equal to malloc. I don't have a hard data type, so I can't use size of here, but I have no reason to. I have been told how big the elements are via the second parameter. So 4 times a lem size. Just use the parameter as opposed to the field inside the struct. I can do a few things to make my life easier. S arrow lems better not be equal to null, or else I don't want to continue, and the assert will make sure of that. I also could benefit by doing this. Assert that S arrow lem size. This one's not as important because it takes a lot of work to pass in a negative value for a lem size. But nonetheless, it's not a bad thing to put there, because if you try to allocate negative 40 bytes, it's not going to work. Okay. That in an implementation makes sense. I think even if it makes sense, there's some value in seeing a picture. It takes this stack right there with its 4 fields inside at the moment. And let's say I set aside, I want to go ahead and allocate a stack to store doubles. That means the lem size field would have an 8 right there. I'd set aside space for 4 of them. The logical length is 0. I'm just making sure this is consistent with the way I've done this. That's right. And then I would set this point to, as far as the stack knows, it has no idea doubles are involved. It just knows that it's a 32-byte wide figure, and it has all of the information it needs to compute the boundary between 0 and 1, 1 and 2, and 2 and 3. Okay? Make sense? As far as stack dispose is concerned, stack asterisk S. This is incomplete, but it's complete for the moment given what I've talked about. I just want to go ahead and I want to free SROLMs and not concern myself yet with the fact that the actual material stored inside the blob might be really complicated. Just for the moment, think ints and doubles and plain characters. But the fact that I'm leaving space there adumbrates that this will change soon. Okay? Let me deal with, actually, let me give it, this has a lot of space. But let me write. Stack push right here. Void stack push stack asterisk S void star a lem address. I'm going to simplify the implementation here a little bit by writing a helper function. I could have written the helper function on the int specific version, I just didn't. Up front, if it's the case that S arrow log length double equals S arrow alloc length, then I want to cope by calling this function called stack grow. And you know what stack grow's intentions are. That looks like an I. Let's make it an S. And then I'm just going to assume that stack grow takes care of the reallocation part. I'll write it in a second. That's not the hard part. Okay? Once I get this far, whether or not stack grow was involved or not, I want to somehow take the SROLM size bytes that are sitting right there and write it into the next slot in memory that I know is there for me, because if it wasn't, this would have been called. Okay? So what has to happen? Let me refer to this picture. Is just assume that this picture is good enough because I obviously have enough space to accommodate this new element. Let's say that I have 3 elements, so that these have been filled up with interesting material. Okay? And I somehow, in the context of that code over there, have a pointer to some other 8-byte figure that needs to be replicated in. Okay? This is going to be the second argument to memcopy. This right there is going to be the third argument. The only complexity is computing and figuring out what the first argument is. It has to be that. It doesn't need to know that it's a double star or a struct with 2 ints inside star or whatever. It just needs to actually get the raw address and replicate a bit pattern. No matter what the bit pattern is, as long as it's the same in both places, you've replicated the value. Okay? So the hardest part about it is doing this. Void star, I'll just say target is equal to car star S arrow LMs plus S arrow log length times S arrow LM size. This is why I demanded all of this stuff to be passed to my constructor function, so it was available to me to do the manual pointer arithmetic later on. Okay? I don't think I messed this up. Log length is right there for the same reasons it was in between the square brackets for the int-specific implementation of this. These are square brackets. Okay? Then what I want to do is I want to go ahead and memcopy. Okay, into the target space, whatever's at a lem address. How many bytes? This many. S arrow lem size. Then I can't forget this. This was present in the other implementation as well. I have to note the fact that the logical length just increased by 1, so that's how I manage that. Okay, you guys see like just the bits moving on your behalf in response to this function? Okay, there's a question back there?
The car star after target, void target equals?
This right here, remember that SROLMs, unless I made a mistake, it's typed to be a void star, right? So you can't do pointer arithmetic on the void star, so the trick, there's actually 2 tricks. I opt with this one because I'm just more familiar with it. You can either cast it to be a car star, so that pointer arithmetic defaults to regular arithmetic. This as an offset, it's still the offset. It just happened to involve multiplication. It is itself implicitly multiplied by size of car, which, as far as multiplication is concerned, is a no-op. Okay, I have also seen people, I think I mentioned this before, I've seen people cast that to be an unsigned long, so that it really is just plain math, and then they cast it to be a void star. Pointers and unsigned longs are supposed to be the same size on 32-byte systems. Okay, a long is supposed to be the size of a word on the register set. So I've seen that as well. You can do whatever you want. All my examples use the car star version, so that's why I use that one. Okay. Okay, the stack grow thing. The reason I want to do that is not because of the mem copying or the void star. I just want to explain what a student asked 2 seconds before class started. You're kind of already getting the idea that the word static has like 85 meanings in C and C++. Okay? Well, here's one more. When you see the word static, decorating the prototype of a C or C++ function, not a method in a class, just a regular function, such as static void, stack grow, and it takes a stack asterisk S. What that means is that it is considered to be a private function that should not be advertised outside this file. Okay? So in many ways, it means private in the C++ sense. Okay? The technical explanation is that static marks this function for what's called internal linkage. You know how you're generating all these .o files? When you type make, all this stuff appears in your directory. Okay, some of them are .o files. I'll show you a tool later on where you can actually look at what's exported and used internally by those .o files. Stack push and stack new and stack dispose are all marked as global functions, and that the symbols or the names of those functions should be exported and accessible from other .o files or made available to other .o files. Something like this is marked as what's called local or internal. And even though the function name exists, it can't be called from other files. That may seem like it's a silly waste of time, but it really is not. Because you can imagine in a code base of, say, 1 million files, that's not outlandish, believe it or not. Think Microsoft Office, the whole thing, probably has on the order of hundreds of thousands of files, maybe tens of thousands, I don't know what it is, more than a few. You can imagine a lot of people defining their own little swap functions. Okay? And if they're not marked as internal functions, at the time that everything is linked together to build Word or Excel or whatever, the linker is going to freak out and say, which version of swap do I call? I can't tell, because it has 70 million of them. But if all 70 million are marked as private or static, then there's none of those collisions going on at the time the application is built. Does that make sense? Okay. This is responsible for doing that reallocation. Assume it's only being called if it understands that this is being met as a precondition. So it can internally just do this. S arrow lems equals realloc. I will not mess this up. I will not mess this up. I always mess this up every quarter. S arrow alloc length times S arrow lem size. After 20 years of coding with C, I forget the lem size every time I write a realloc request. Okay? Make sense? That's the cleaner way to write it, I think. Okay? It makes this focus on the interesting part that's hard to get and kind of puts this aside as uninteresting. Okay? There's that. Algorithmically, the function that's most different from the integer version actually is this stack pop call. This is how I want to implement it. Void stack pop. I'm popping from this stack right here. I'm placing the element that's leaving the stack and coming back to me at this address. There's no stack shrink function to worry about. So what I want to do is declare this void star, not called target, but called source. Actually, that's right, yeah. Is equal to car star of SROLMs plus SRO log length minus 1 times SRO LM size. I forgot to do the minus beforehand, so I recovered by doing a -1 right there. Okay? This is where we're drawing a bit pattern from in the big blob behind the scenes. We're drawing bit patterns from there so we can replicate it into a lem address. A lem address is the first argument. I'm copying from that address right there. How many bytes? This many. And then do what I should have done earlier. Log length minus. This really should have been the first line, and I shouldn't have the -1 there, but this is still correct. Okay? You guys get what's going on here? Do you understand the helicopter basket analogy? Okay, where I'm actually identifying a space where it's safe to write exactly one element, so that when the function returns, I can go, wow, that's been filled up with an interesting element to me. Okay, and I can go ahead and print it out, or add it to something, or replace the 7th character, or whatever I want to do with it. Okay? This used to be int. Okay? If I wanted to, I could have punted on this right here and just passed in one argument, and I could have returned a void star that pointed to a dynamically allocated element that's a lem size bytes wide. Does that make sense to people? Okay? And I just would have copied, not into a lem address, but into the result of the malloc call. With very few exceptions, malloc and stirdoop and realloc being them, you usually don't like a function to dynamically allocate space for the call and then make it the responsibility of the person who called the function to free it. Okay, there's this asymmetry of responsibility, and you try to get into the habit as much as possible of making any function that allocates memory be the thing that deallocates it as well. Okay, there's just some symmetry there, and it's just easier to maintain dynamically allocated memory responsibilities. Okay, it's not wrong, it's just more difficult to maintain. It actually clogs up the heap with lots and lots of little void stars pointing to pointing to blobs of S arrow lem size bytes, as opposed to just dealing with the one central figure that's held by the stack, and then locally define variables of type int and double that are passed in as int stars and double stars, recognized as void stars. But because we laid down the right number of bytes, as long as everything is consistent, we get back ints and doubles and things like that. Okay? Yep.
In this case, do you have to void star element address it's like your basket, right?
Yeah, but I'm not actually changing a lem address. I'm just changing what's at a lem address. So let me actually make a sample call to this. Suppose I have a stack S, and I called stack new with ampersand of S, and I pass in size of int. Okay? That means that I have this thing. That's my stack, and I'm supposed to just take it as a black box and not really deal with it. But I know behind the scenes that it has a 4 there, and maybe my stack has 14 elements in it, and it can accommodate 16 elements, and that it points to this thing that has not 2 or 4 or 8, but 16 elements in it. Okay, and I'm like, you know what? I did all this work and I pushed on 14 elements right there, but I'd like to now pop off the top element. When I do this, stack pop, I have to pass in that. I have to pass in the address of an integer. Okay? Does that make sense? So the stack pop call has a variable called a lem address that points to my variable called top. And it relies on this variable to figure out where to write the 13th, or the element at position 13. It happens to reside right there. Okay. The memcopy says, where do I write it? I write it at that address right there. It would replicate this bit pattern in the top space. This returns, and I print out top, and that corresponds to the number 7300 or something like that. Okay. If I really wanted to change this void star, I don't change the void star anywhere. I just use it as sort of a social security number or an ID number on the integer. Okay. If I really wanted to change this, you'd have to pass in a void star star. There are scenarios where that actually turns out to be what you need, but this is not one of them. Okay. Yep. Yeah, go ahead.
For this pop, like let's say that this function doesn't work, right? Let's say we're copying the wrong stuff. How do we test to find out if we pop what we wanted to pop? Like for instance, let's say you wanted to pop something that was an integer,
Yeah.
and then you pop it, you bring it back, and then what if there was something wrong with the resize thing? Can we like set that thing that we just popped to like no or something, and then
You could. If you have, if you really want to exercise the implementation of the stack to make sure it's doing everything correctly, you'll write these things. You may have heard this called what are called unit tests, which are usually implemented. There's two different types of unit tests. There's those that are written on the .c end, which know about how everything works, and then there's those that are written as a client to make sure that it's running as it's behaving like you think it should. If that were the case and you wanted to protect against that, you could write all of these very simple tests to make sure that things are working. Think of some unit tests as a client. You might for loop over the integers 1 through 1,000,000. Okay? You might actually set the initial allocation length not to be 4, but to be 1, so that you get as many reallocations as possible. You could for loop and push the numbers 1 through 1,000,000 on top. In a different function, you could actually pop everything off until it's empty and make sure that they are descending from 1,000,000 down to 1. Okay? And if it fails, then you know that there's something wrong. If it succeeds, you never know that something is completely working, but you have a pretty good evidence that it's probably pretty close if it isn't. Okay? You can change the implementation to kind of make sure that all of the parts that are really risky, like the reallocation and the minus minus and the memcopy calls, are working. One thing you could do, and this actually, assignment 3 takes this approach a little bit. Right here I use this doubling strategy. If I really wanted to test the reallocation business, I could actually do a ++ instead of a ×2 on the allocation size and to reallocate every single time. Not because you want it to work that way, but because you can just make sure that algorithmically everything else works regardless of how you resize stuff. Okay? Does that make sense? Now, another answer to your question, if I didn't take that approach with the unit test answer, is that when you're dealing with generics in C and void stars and memcopying and manual casts, you have to be that much more of an expert in the language to make sure that you don't make mistakes. It's very easy. Think about this way. I know you're not going to believe this yet because you haven't coded in C that much, but assignment 3 you will. I know how most of you program. You write the entire program and then you compile it and you have 5,500 errors and you get rid of them one by one, okay? And it takes you like 3 days, and then it finally compiles and you run it, and even if it doesn't quite run the way you want it to, it rarely crashes. Okay? I mean, most people don't even know what the word crash means until they get to 107. You will next week, trust me. Okay? As far as C++ is concerned, because it's so much more strongly typed than C is, it is possible for you to write an entire program, to have it compile, because compilation does so much type checking for you in a C++ program that uses templates, okay? It's quite possible that once it compiles, that it actually works as expected. It doesn't happen very often, but it's certainly possible. In a C program where you're using void stars and char stars and memcopy and memmove and bsearch and all of these other functions you're going to need to use for assignment 3, it's actually very easy to get it to compile. Because the compiler's like, oh, void star, yep, I can take that. Yep, that's fine. It just does it on all of the variables. And so it compiles, and you're like, good. It wasn't 3 days. It was 1 day. And then you run it, and it crashes because you did not deal with the raw exposed pointers properly. So that's what makes certainly the first assignment in Pure C with dealing with void stars difficult. But there's an argument that can be made to say that it's very hard to get all this stuff right every single time you program. I've already told you that right here, I forget this S arrow lem size probably 1 out of every 2 times I teach this example. That's because it's very unnatural compared to the C++ way of allocating arrays to think in terms of raw bytes. And you think in terms of sizes of the figures, you see the pictures in your head as to how big things should be, so you just remember that number right there, but you forget about this. If you forget this right here, it compiles, it runs. If you're dealing with integers, then your array is 1/4 as big as it needs to be to store all the integers you want there. Does that make sense? Okay. You will learn this and feel it at 11:59 a week from Thursday. Okay? All these types of errors, because it's going to compile and it's going to run very often, but occasionally it's going to crash and you're not going to know why, and you're going to say, oh, it's the compiler. It's not. It's your code. Okay, so we will talk more on Wednesday. Okay?